In this video, we will see how applying the Aufbau principle and Hund's rule can actually lead to incorrect electron configurations. And so, in other words, we are going to be identifying some common anomalies in writing electron configurations. The most common examples of anomalous electron configurations that are cited involve chromium and copper. The actual electron configuration for chromium has the argon core of 18 electrons, plus 1 electron in the 4s subshell and 5 electrons in the 3d subshell. So the argon core, 4s1, 3d5. Now if we followed the Aufbau principle of filling the lowest energy subshells first, we would expect the electron configuration to be the argon core, 4s2, 3d4. Similarly with copper, the actual electron configuration for copper is the argon core, 4s1, 3d10, instead of the argon core, 4s2, 3d9, which is what we would expect if we followed the Aufbau principle. So let's use our orbital diagram for multi-electron atoms to see if we can get our heads around why this might be the case. The first thing we should note is that the anomalies only start to occur in third period elements beyond the noble gas argon, which is the element number 18 on the periodic table sitting at the end of period 2. So we will start by populating the orbital diagram with the 18 electrons of argon giving an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, or a condensed electron configuration of the 10 electron neon core, 3s2, 3p6. When we go to element number 19, potassium, we must remember that the 4s subshell lies lower in energy than the 3d subshell. And so, according to the Aufbau principle, the 19th electron for potassium must be placed in the 4s subshell, which is also the 4s orbital, giving an electron configuration for potassium as the argon core with the additional 4s1 electron. When we go to element number 20, calcium, we add a second electron into the 4s orbital, spin paired, to give an electron configuration for calcium as the argon core, 4s2. According to the Aufbau principle, the next highest subshell that needs to be filled is the 3d subshell. So if we go from element number 20 to number 21, scandium, we add the 21st electron into that 3d subshell and we get the electron configuration for scandium as the argon core, 4s2, 3d1. Adding another electron gets us to element number 22, titanium, which has the electron configuration of the argon core, 4s2, 3d2. Adding another electron, we get to vanadium, number 23, with an electron configuration of the argon core, 4s2, 3d3. Adding another electron, and we get to chromium, element number 24, and we would expect it to follow the same pattern and have the argon core, 4s2, 3d4. And that's what the orbital diagram is showing at the moment, and that's what we would expect by following the Aufbau principle. But as you can see here, the correct electron configuration is actually the argon core 4s1 3d5. So it appears that one of these 4s electrons here actually prefers to sit over here in the 3d subshell to fill the 5th orbital, so that we end up with a half-filled 3d subshell. And it turns out that half-filled subshells have an added stability associated with them, so that the argon core of 4s1 3d5 is actually a more stable electron configuration than the argon core 4s2 3d4. So what we've got now is a situation with that s electron moving over into the d subshell. The orbital diagram now matches the electron configuration shown on the right-hand side. If we continue to add electrons, we get to element number 25, manganese, by placing the next electron in the lowest available orbital in terms of its energy, and that is the 4s orbital. And we get the electron configuration for manganese as the argon core, 4s2, 3d5. And so we're back on track as to what we would expect according to the Aufbau principle. We can now continue to fill the rest of the 3d subshell by adding a 26th electron, which needs to be spin paired with another electron in the same orbital. And this represents the element iron with an electron configuration of the argon core 4s2 3d6. Adding another electron, we get cobalt, number 27, with an electron configuration of the argon core 4s2 3d7. Adding another electron, we get to nickel, number 28, with an electron configuration of the argon core 4s2 3d8. Now when we get to copper, number 29, we see that the orbital diagram shows that According to the Aufbau principle, we would expect an electron configuration of the argon core 4s2 3d9. But the actual correct electron configuration that is most stable is the argon core 4s1 3d10. And again, it's as if one of these electrons in the 4s subshell at the top left actually prefers to sit over here in the 3d subshell, this time to complete a full subshell. And again, it turns out that filled subshells, like half-filled subshells, have an inherent added stability about them, so that the electron configuration of having an argon core 4s1 3d10 is actually more stable than the argon core 4s2 3d9, which would be the one we would predict according to the Aufbau principle. So finally, we can go on and add a 30th electron, which would go into the 4s subshell, being the lowest energy subshell available. And we get the electron configuration for zinc, number 30, as the argon core 4s2 3d10. And so we're back on track as far as what we would expect from the filling of subshells in the orbital diagram according to the Aufbau principle. So filled subshells and half-filled subshells have an inherent added stability, and they are therefore responsible for these anomalous electron configurations that we see for chromium and copper. Now, there are other examples to add to the more common examples of copper and chromium, including silver, gold, palladium, and molybdenum. And again, we can see that the actual electron configurations deviate from what we would predict by using the Aufbau principle due to the fact that it is more stable to have half-filled D subshells with 5 electrons in them, as in the case of molybdenum and chromium, or completely filled D subshells with 10 electrons in them, as in the case of palladium, gold, silver, and copper.